next up we have Jason Larson from IOActive. If you haven't seen Jason's Triangles talk, although I assume from the laughter that everyone has, you might be interested in the title of this talk, which is Triangles Reloaded. Jason Larson worked for Idaho National Labs for almost a decade, right? Doing security assessments on major energy management systems, as well as specializing in cyber physical damage. Jason now works for IOActive. I think you're a principal consultant, or yeah. Okay. So yeah, Jason has also done a lot of chemical work. He also did modeling of neutron beams to help treat brain tumors as one of his side jobs, and has also written software to analyze nerve impulses, worked on intrusion prevention systems, and was spent 2 years on the Windows 7 penetration team. So he's a really smart guy. So take it away, Jason.
Okay. Everybody's putting kitty cats on their slides for the protected process, but I'm kind of a shoot the kitty cat kind of guy. So this will be a little bit more on the offensive side, although it's going to be hard to follow Marina. So happy things. So last year I talked about building WaterHammer by cycling a valve and getting a pressure transient that gets bigger and bigger. So the happy things, built the big 60-foot rig, successful. Sad things, the results are still under embargo, so I can't tell you about those things today. So I'm going to have to tell you about something else. So just as a quick background, I have a friend that's a mechanical engineer, and he says there's two answers to every question. There's a technician answer, and there's an engineer answer. So the technician will tell you if something is going to go up or down, and the engineer will tell you by how much. So in this case, if we have a bucket with a bunch of holes in it, the technician answer is, yeah, it's going to drain out, and the things on the bottom are going to drain last. And the engineer will say, like, it's going to drain in 20.4 seconds, and the curve of each one of these, the pressure curve of each one of these holes is going to look like this over time. That's the technician answer versus the engineer answer. So when you're exploiting a process, attackers are generally drawn towards things that they can do that they only have to know the technician answer to. So it's much easier for an attacker to come over there and say, kick the burner on and leave it there until something breaks. It's much harder for an attacker to come over there and say, like, okay, well, heat this up to 106 degrees and then add exactly this amount of chemical, get the proper reaction and all that stuff. So the technician answer is really hard, and attackers kind of like or the engineer answer is really hard, and they like the technician answer. Although sometimes we can actually turn a technician answer into an engineering answer. So in World War II, they were flying some bombers into Germany to break out some dams, and they tried to teach the pilots to fly at a particular height so they could come over there and drop these little canisters exactly at the right time, drop them in and kill the bombs. And they really just couldn't do it. So until somebody came over there, they grabbed two spotlights, pointed them towards each other underneath the plane, and said, just fly and make the two circles in the spotlight overlap each other. And then they were at the right height. They could drop the stuff off, and they didn't have to do the precise looking and calculating and everything to get this going in. So a lot of times when you're designing an attack, you can actually turn a technician answer into an engineering answer by cleverly using all these side effects, what's bigger than the other, because you'll see these swap points. So if we have a process out there, a lot of times the process is a little bit hacker unfriendly. So we don't know why these lazy process engineers out there decide to design processes that don't have all the data necessary for a particular attack just sitting there waiting on some sort of sensor so that you can read off exactly what you want. But they tend to be lazy, and we're going to have to do something about that. So for example, let's take this particular diagram. So Marina, who was just up there stealing lots of the Triangle Thunder today, proposed some catalyst poisonings where she's going to basically run the loop around and make you run through your expensive chunk of platinum inside this process over and over again. But in this particular process, we've got a couple of, let's see if I have if I have a button for this. Down here below, we have a couple of measurements on the X of the reactor. We can measure the flow rate and we can measure the temperature, but what we really want to measure is the percentage of the chemical that's getting reacted per pass. So this is what we actually have, and we want to know some other value to pull off the attack. So in this case, we need to start looking at proxies, or what I call sensor proxies. So it's common when you're designing a process to make statements like, in this case, the temperature I'm measuring over here can be used as a proxy for the pressure, because I know temperature and pressure are related by this particular equation, so I can measure one and I can calculate the other. So when we're looking into a process, then if the data is not available, we have to find creative ways to go out and get the data or estimate the data. We can solve some of these missing value problems when it's coming up. So the question is, for each one of these sensors, it's not what the sensor is designed to measure, but what it can actually measure. And sensor proxies are everywhere because all your sensors are based around a set of physics, and physics are all interrelated and correlated. So if we can measure one part of the physics, we can estimate the rest of it. So let's start down in the physics layer. So maybe if we come over there and we get down into the actual sensors, we can get these sensors to tell us some new things. If we look at a sensor, then a lot of times, if you look at a particular sensor, it's tuned to measure a particular aspect of the physics, and then everything else is noise. But if you actually go look at the noise tells you something else about the process. So one man's noise is another man's data. So the actual physics are more interrelated than we usually think about. So if we take a typical LED, an LED is always a light sensor based on the physics. So if you take an LED and pop it out of there and have it stop shining light, then hook it back up with some voltage on the other side and shine some light back on it, every LED is actually a photodiode. So it's the same component. Anytime you need a photodiode in a circuit, you can always just yank out an LED, slap it on a board, and it's a photodiode. So I thought I would actually build a test rig for this and show everybody what sensor proxies are like. And I had a nice chip all lined out that's used in a bunch of industrial control stuff that I turn into a microphone so I can listen to people after I've hacked into the process and hear the engineers talking about things and all that type of stuff. It's great fun, and I've used it for years. But it's a little bit too easy to figure out which vendors use that particular chip, so I decided to go a different way and actually go find another sensor proxy that gives me audio. So what I did was I took a Dell monitor and I ripped apart the Dell monitor. And after you rip apart the Dell monitor, then you get this little board here out of the side of it. And so this particular one, when you go to interact with the menu on the front of it and your hand comes close to it, the lights all light up on it before your hand ever even touches the monitor, because it's actually a capacitance sensor. So what you have in there is something that's designed to measure the distance and how hard you're touching the buttons, but it's really a capacitance sensor. So I tore it out. I did lots and lots of searching until I found a spec sheet for the chip. And I did what I did for the other chip, is I went in there and I turned the sensitivity all the way up and said, yes, make these capacitance sensors as sensitive as possible. And then I started pulling the data out of the result register and watching the fluctuations and the capacitance of this just while it's sitting there on the desk. And so I looked at it, and it's like, how fast can I pull this data? It's like, woohoo, I can pull this data at 600 kilobits a second. That's totally fast enough for sound. I'm like, yes, this is all going to work. I'm going to have an awesome S4 presentation. I'll put a monitor up on stage and record some voice. It'll all be great. But unfortunately, after I looked at the data a little bit closer, I can pull the data at 600 kilobits a second. As I'm pulling the data, you can see that lots and lots of these things are actually repeated. So the internal state of this particular register wasn't updating fast enough for me to get useful data out of it. So you get really, really, really bad data. So if you can hit that audio file there. So I took basically a scale out sound. And so this is this is the audio being recorded, really, really, really bad audio, off of the button sensor that's on the front of your monitor. This is also on a bunch of keyboards and stuff like that, so your monitor can sit and listen to you really, really badly. But sensor proxies are a lot of times like that. Once you get in there and you're like, haha, I'm totally going to get the data that I want, then you find out the data is kind of bad, but a lot of times it's good enough for basic detection of the state of the process, detection of what's going on, and various other aspects. So with a lot of these particular things, the vendors actually kind of partially document which one of these things you can use as a proxy for another sensor. So if you go look in this, they'll say like, oh, well, this is a really great sensor, except you have to compensate for, in this case, atmospheric pressure. So if atmospheric pressure is the noise on this sensor, you can say like, well, if I eliminate everything else, the noise I actually see on the signal is atmospheric pressure. And so there's tons of sensors that you go and then just read the spec sheet. It's like, oh, well, you must correct for temperature. Okay, this can be used to measure temperature instead of whatever else is measured. You must compensate for pressure. You must compensate for everything else. So those compensation factors turn into the sensor proxies. So let's pop up a layer. So we've got the actual sensors themselves and the physics, and that's all really nice and good. But let's actually look at the boards. Well, the function of all the pins on a lot of these microcontrollers actually aren't set. People build microcontrollers, they have a whole bunch of different functions, and you select those functions into various blocks that do analog to digital conversion. You can make inputs, outputs, all that's done in software. So the purpose of that's actually every pin isn't actually fixed. This is actually getting a lot more complex than it used to be. So if we look at this particular chip I have up here, this is an MSP430. If you look at this pin right here can be a digital output, it can be a digital input, it can do analog to digital conversions, and also can trigger an internal BIM copy inside the chip. So when they designed the board, the software comes over there, configures this chip, and runs it for more normal operation. But we can actually reconfigure this in a number of different ways. And if we get lucky, we actually start reading those things. Like when we have the LED is actually a photodiode. Well, the digital out's going through and it's powering this LED and we get nice blinky lights. But what if we switch the power around through the other way? Well, this LED now starts acting as a photodiode, and we can actually start looking at the light coming in through the photodiode. And if that other pin happens to be, the input pin happens to be one of these ones that we can turn into analog to digital conversion, we actually have a really, really good light sensor. And so right now you have to kind of get lucky for these types of things, that whoever took all the traces out and hooked up all the physics to this particular microcontroller, that they happen to use the pins that are useful to you. But this is actually going to get way more common in the future because a lot of the manufacturers are starting to go to circuit under pad, where they want to be able to sell you, instead of this chip has one SPI port and one I2C port. They're like, oh no, we have an SPI unit, and you can have 8 of them if you want. You just select all those pins into all the different units. So all the different pins on the chip will be able to do all the different functions, which means that as an attacker, you can get in there, get on the chip and say like, oh yes, turn this one into now an output, and turn this one into an analog to digital conversion, and pulse this one with a pulse wave modulation. And you can start interacting with the actual physics of the sensor in new and interesting ways to pull out more data. So we'll go there since we're running a little bit behind. Okay, so after we get into all the sensors, we've got we've hacked onto the physics, we've hacked onto the boards, we can actually get data from other parts of the process. So once I came over there and I grabbed this pump and this sensor and everything, I stuck them together with a bunch of pipes and I built a process. All of these sensors are related by the physics of the process. So by looking at the physics of the process, I can start inferring what other things are doing by the sensors I actually have access to. But how do we go about that? So if you look at Marina's paper, she showed that the process just doesn't stop when the control system decides to stop talking to it. So she showed with a denial of service, we can denial of service some sensor signals, and the process will continue reacting on its last bad data. Other things that you look at is like Boyle's law, relates temperature, volume, all those types of things. So we can go look at those and start figuring out where the proxies are. But the relationships are actually really complex. That's why we have modeling software that does lots of things. And so it's usually not as easy as one simple calculation to relate that value to the other value. So how can we actually start doing this. So the best way to do this, of course, is triangles, because triangles are the answers to all things. Okay, so here we have two sensor signals out of a process. And these two sensor signals are correlated. So you can see the peaks and the valleys just kind of roughly match up, et cetera. But they're also shifted in time. So one of these things happens before the other one of these things. This is the direct correlation that we're looking for to start building a proxy for whatever value we're trying to do. So the traditional way of doing this is to grab all this analog data and run it through some least squares regression mathy things and try every possible combinations and build nice graphs. And we can see that in this case, like signals 13 and 16 are highly correlated. But we're going to be hacking into a process. We're going to throw in a bunch of software on there, and if we start doing this high-level recursive math over large matrices and stuff, somebody actually might notice. So we can't really do it the traditional way. So lots of CPU time and memory, and also we have other problems. So one of the problems we have is dead time. So when an actuator comes up and says, hey, go change the process in some way, the process doesn't immediately change. So like you have the big pot of water over there and you say, kick on the burner. Well, it's not instantly hot. It's hot sometime in the future. And so you have this dead time before it starts reacting, and you have a rise time. So if we go look at that, we actually need a new form of triangles to start dealing with all these sensor signals as we come in. We've got to deal with the dead time, the rise time, et cetera. So I actually tweaked on my algorithm a little bit and came up with a new type of triangles that kind of works on this. So in this case, instead of using line segments to estimate the peaks, I actually use line segments to, let's see, which button here is the actual pointer? Aha, there it is. Whoops. So we come over here and we have the line segments that would estimate the peaks and valleys. That's basically like I described last year. We can also tweak an algorithm that connects the point of inflection of each one of these curves, basically the min point. So I tweaked an algorithm that tries to connect the halfway point, the half power point between the point of inflection and the minimum and maximum. And that creates these horizontal bars that you're seeing here. So we're basically taking and drawing a straight line, a flat line, from the half point of the last curve, the half power point of the last curve, up through to the half power point to the next curve. So this actually becomes useful in a couple of different ways. So if we actually look at the slope of the line between the two half power points, that's useful for a correlation. And if we actually take the flat lines, that's actually useful for dead time. So if we're looking inside the process itself, then near the peak values, this is when you have the least certainty about the correlation. Things are changing your process. Some disruption just happened. It's working its way through your process, and we haven't seen the results of those. Those are the peaks and valleys. So right there at the inflection point, right in the middle of it, this is where we have the most certainty about what's going on in the process. Things are progressing nice and linearly. The actuators are kicking in. The feedback loops are doing their stuff. We actually have good correlation. So this is what a complex sensor signal looks like when you apply this new algorithm to it. We have a line segment. We're chopping off these areas of uncertainty on the top and bottom, and we have flat levels of relative calm inside the process. So when we're detecting the correlation, we take all our sensor signals and we run them through this new triangle algorithm. We're going to get a bunch of sequences, A, B, C, and D, that it'll draw over and over again, because that's what the algorithm does through each of the sensor signals. So we actually take and we take this in the sequences, not in time spaces or frequencies or any of the other stuff. If something goes through A, B, C, and D, in about the same time frame, something else goes through A, B, C, and D, we can kind of start to say that these two sensor signals are correlated with each other. On the other hand, if it runs through A, B, C, and D at a different rate, we can say that this sensor signal is uncorrelated with the other sensor signals. So then we can actually relate the rising slope in AB to another AB, and we can do just some simple math, and we can say like, oh, if we're this far along the slope, then that's about this far along the other slope. And we can start correlating the measurement of one sensor signal to the other sensor signal. So after we grab all this stuff together and we do a whole bunch of mathy stuff and we find the correlations, if we start overlaying this back on top of the process over here, we can see then that certain sensor signals follow each other, and they follow each other in time. So when this actuator over here rises, then at a certain time delay, we'll actually see changes in the temperature and the pressure over here, and some changes in all the other stuff. And then in a different correlated signal, we'll see these same relationships. So this starts letting us build a technician-level model of what the process is doing. We don't know the engineer answer for why it does all this stuff. We're just observing that when this goes up, then there's a delay, and that goes up, and there's a delay, and the other thing goes up. So in the whole process hacking, SCADA hacking stuff, then a lot of times you come over here and to build this minimal process model. So what we can do then is we can take all these correlations, run them through there, get a bunch of line segments, and then turn that into this minimal process model that tells us about what's going on inside of the process. So we can use that model then to go and look at the state of the process. A lot of processes are only vulnerable when they're transitioning between particular states. So we can then use this technician level model to detect when it's in the vulnerable state, and then afterwards we can actually then play it back to do all the spoofs on the operator screens and all of that type of stuff. So we also have bad correlation detection. Once you're into the actual attack phase of the process and you have multiple signals that all correlate back to the thing that you want to measure, you can actually calculate fairly simply if all of your sensor proxies still agree that you're somewhere in the range. As that starts to diverge, we can come over there and say the process has done something funky, and we're now in unknown territory, and it's time to bail out of that. So you also have transient correlations. So some things are nice and linearly correlated, but other things come and go. So one of the things that you can use to look at is, say you have a pump in a pipe. If the pipe is already pressurized, that pump's going to come up to a speed faster than the pipe's not pressurized. And so if by looking at how fast the pump comes up to speed, you can actually then infer what the pressure in that pipe was at that particular time. And so you can actually tweak some of the algorithms and look at the initial rise and fall times, the startup times of various sensor signals, and from there infer the value that you actually need. So this approach actually does come with some pretty severe limitations. So Sergey Brodis said that all exploitation is unexpected computation. And so he said, well, when I exploit something, it executes something that it was unexpected. And so hacking processes can be described as unexpected physics. And with sensor proxies as well as all SCADA attack, then the unexpected physics is an interesting case because as you reach this unexpected physics, the process is now doing something it's totally not designed to do. Then our measurement of the process during those phases is going to be unknown. So pretty much all of the algorithms here, as you're playing them back, are going to be really awesome until you actually start tweaking on the process. And the process is going to do something totally unexpected, and all of your measurements are going to be totally invalid. So trying to understand what sensors are going to do during the unexpected physics, I think, is part of the future of process control hacking. So future research. So now that we have all this awesome stuff and we can start building process models and using them to do cool spoofs and everything else, then there's a few things that I've been working on. One is when we actually did the correlation detection, we actually looked at it, ran through the ABCDs of the algorithm in a particular sequence. And because a process is a sequence and not a frequency, we can actually describe that frequency as basically just a set of symbols. So down here we have the set of symbols that we talked about earlier. One of the things that's really awesome about sets of symbols is that you can describe any set of symbols using a Berle-LeCamp-Massey as a single linear feedback shift register, basically a random number generator that just happens to generate the things in the order that you did. So it may be possible that during the attack phase of a process, you may be able to do all the process detection in the detection phase by pumping a single linear feedback shift register that says the next thing you should see is this thing should start rising. Then the next thing you should see is this thing flattens out. The next thing you should see is this thing falling. And you should see it rising and falling at this rate. And we may be able to do that in a single linear feedback shift register. So it can sit there very, very, very small in code and sit there and pump it. And then we can use it as detection, saying what is the state of the process and how well does that match the random stream of stuff coming out of my LFSR. And then during the attack phase, you can pump that and then generate all the nice operator screens that are all fuzzy and look like they're supposed to and all that type of stuff. So we've broken all this stuff down to a set of line segments. So this comes into, means that we may be able to just apply a bunch of linear algebra to do all this stuff in a much more awesome way. Anybody that's played with matrix transformations, there's always transformation matrix, and there's always things that come out of there that are unaffected by the matrix. So one of the things I've been playing with that I have not yet succeeded on, so we can take the entire process of generating the triangles, correlating the triangles, and then playing them all back, and describe that all in a single set of matrix manipulations. So the sensor signals come in, we multiply them by a matrix over and over and over and over again, and it will do all of the work in a very, very simple mathematical way. Why is this awesome? It's awesome because then we can do, in a very, very simple way, we can build firmware implants, we can stick it in ladder logic, we can stick it in IEC 61131 virtual machine, and it can do all of its work in the background in lots and lots of different ways, and can be repurposed over and over again. So, so this is the end of my presentation, so I think I have a few minutes for questions. I've done a perfect job.
Yep.
Hi, this is Mike Tucker. Could you pick up radio signals with something like this?
Sure, definitely.
So low frequency signals, something like that, like sent from a big array somewhere?
Yeah, but if you have RF retroreflectors, why would you bother, right?
Just curiosity.
Yes. Yes, if you were looking at it as a command and control channel, you can turn lots and lots of different sensors into really, really good RF antennas with just a software update. Oh.
So when you were looking at the capacitive sensor, and you were going through the iteration on it, did you think it's more of a problem of the sampling rate of the equipment? We're talking about the sound, I guess.
Oh, okay.
So have you looked and see, is it like a sampling rate issue on the hardware, or is it more just, it just can't take the amount of cycles that you're trying to pull out of it?
Yeah, so the problem is what I think is going on inside this chip is the chip's got an internal clock that has two clocks. One is the I2C bus you're using to query what is the pressure value on all of these sensors on the front, and you have a second clock that's actually going out and querying the pressure values. And so I can actually say what's the value of the register much faster than it's actually going and getting the value of the thing. So I hope I can actually find the firmware, a firmware update for this chip laying around, because that may just be a firmware tweak where you can throw a new firmware update in it and actually go query the values of the sensors much, much faster, which would turn it into a nice audio device, and then your monitor can listen to you, sing in the shower or whatever.
Towards the end, you were talking about matrices of sensors. Is your eventual goal to get to a point where you can gather data that the individual sensors wouldn't be able to individually pick up and correlate them using linear algebra?
Yes, so that is the end goal, is that we feed all of the data into the sensors and we come up with a correlation matrix. The correlation matrix is only going to tell you the technician answer. That it just so happened that the slope of this curve in response to this disturbance in the process is 3 seconds later you see this slope pick up after it. So it's only going to tell you that technician level answer. It's not going to tell you the physics of how these things are related. Just say these are related, and this happens to be how they're related linearly. So you could also do it non-linearly. So yes, that's my goal, is to get all of that done in a single set of matrices that you can just pump.
Marina Krotofil from European Network for Cybersecurity. So what are our options as a defender? So how can we make your job harder from the signal processing point of view? Like, can we shift the signal more, like phases, and from the hardware point of view? Are there any recommendation? How do we start designing tools? Because you told like it's not about what it is measuring, but what it can be made being measured. So should the designers of the instruments start thinking about the design of the instruments? So there are 2 points, yeah, 2 questions.
Well, I think, I mean, one of the reasons that I research all of this is there's very little data about, I mean, most SCADA hacking right now is the underpants known problem. It's like, I'm going to hack into a SCADA network. It's like, great, and then what am I going to do? Well, I'm going to do some stuff, and then I'm going to get tons of profit and all that type of stuff. So I would like to see the community start focusing more on the bread and butter of how people are going to go about discovering what's happening in the process and building up all of this stuff. Because just like when we started exploiting operating systems, people are like, oh, code review, we'll do better code and better code and better code, and we still found buffer overflows everywhere. Here it is, 2015, and I think Adobe just had another half dozen overflows in their Flash player announced. What really hurt everybody was address-based randomization, data execution protection, all of those types of stuff. If we start looking into demanding views into the firmware, demanding views into how our sensors are actually configured and work, looking into how attackers are going to go assemble all this data together and actually build their attack. This is a really big window where the defenders can actually see all this activity and then respond to it, rather than something just magically is supposed to be showing up already pre-programmed for all the nasty things it's going to do to the process and taking over the world. There's definitely going to be a phase in the middle there where they can be detected.
Okay, well, thank you very much, Jason. That's great.
Okay. Oh, thanks.